Okay, so welcome to part 2. Now, there are some instances whereby there could be an error of measurement, whether it's in the dependent variable or whether it's in independent variable. So now let us look as to how does the OLS perform in the context of error of measurement. Now, let us start with the context of the dependent variable. So let us say usually if there is an error of measurement in the dependent variable, then that means that we will have a mismeasured value such that that will be a sum of true value plus the measurement of error. So if we assume that, and now let us say y star is, this is our population regression, and then this is our estimated regression. So if this is the mismeasured value, and this is our population regression. So the one that we estimate would then obviously be, your would definitely then include that mismeasured error, and so therefore the error term will be mismeasured. So and therefore that brings us to understand that the consequences of having a mismeasured dependent variable will actually lead to less precise estimators because of the high error variance. And then secondly, is that okay, the OLS will still be unbiased and consistent, so for as long as the measurement of error is not related to the explanatory variables. At least that is one of the positivity that we can take out of here. But the major consequences is that our estimates will definitely be less precise because of the overestimated error variance, or because that error variance includes the measurement or the mismeasured value. Then what happens if it's actually the independent variable which is mismeasured? So if we take x1 to be equal to x star, so this is basically for the population. So let us say now, so that would actually say the estimated x1, and that means that x1 will actually include a mismeasured value of e1, which is the mismeasured value. So again, we say it's a true value plus the measurement of error. So if this is our population regression, remember that x is one of the regressors. So then that means that this estimated x will have problems, and also it means that our error term will also again have some mismeasurement because of the measurement of error in the independent variable. Why? Because remember that we are saying our classical errors in the variables assumption is that, of course, we are saying the error is unrelated to the true value. So in other words, because here we know that this x star, which is the mismeasured value, does not relate to the sample one, right? But now we know that but now what we know is that because of the mismeasured variable xi, which is correlated with the error term, we are going to have that situation, because we are going to have whereby the covariance between x1, which is estimated, with the e1 will be equal to the covariance between the xi, which is the mismeasured, in relation to E1, plus the covariance between E1 and E1. Okay, now, so, and therefore that means that E1 varies, and that's why, because if it didn't vary, then you'll just have sigma squared with no subscript. But because of the variation of the error in the variance, so you will have E1 appearing here, and so therefore the um, variance, or the error term, actually vary and has a high vary. So, and that's why we are basically saying the covariance between xi, obviously here we have mu minus beta 1 xi, which is basically what we have, which is the error term for the estimated regression. Because remember that this whole thing is the error term for the estimated regression. Okay, so is the two are correlated, and so therefore that's why you have beta 1 varying with E1. So, and remember that beta 1 is a coefficient of x1, so meaning that that estimate beta 1 will not be precise because it's definitely affected because of the mismeasurement of error. And that's why the mismeasurement, or the mismeasured variable x1 is correlated with the error term because of that relationship. So we know that the consequences of the measurement error in explanatory variable are as follow. We know that obviously under our assumption is that obviously we will have a situation whereby OLS will be biased and inconsistent because of the mismeasured variable. Okay, and so and that's why it remains inconsistent. Okay, it remains inconsistent um, uh, because of the fact that um, the x1 relates to the e1 and the x star, which is mismeasured. Okay, so and that's why you have that this estimated will actually be equal to the true one, which is beta 1, and we know this relationship. Okay, so and then the second issue is that the effect of the mismeasured variable suffer from attenuation bias. Now, what do we mean by attenuation bias? We are basically saying that the magnitude of the effect will be tending towards zero. Okay, so meaning that there will be an underestimation of the absolute value. That's basically what it means, that you'll have an underestimation of the absolute value. And then obviously, then lastly, we actually know that the effect of the explanatory variable will be biased. So the effect that will be portrayed by the explanatory variable will actually not be true. It will be biased because of the estimated beta 1, which is actually biased. Okay, we also know that sometimes we have an issue with our sample, okay, where we have missing data. This can only become problematic if the missing data has got to do with the dependent variable. But if it's got to do with an independent variable, um, it should not be a problem because it's usually uncorrelated with the error term of the regression. But in terms of the dependent variable, it definitely is a problem because especially if it's based on the dependent variable or on the error term, because this becomes an endogenous. Now remember, the reason why we say the word endogenous is because the dependent variable is being determined within the model. In other words, we are trying to find the expected value of the dependent variable given the fixed values of the independent variables, and that's why we say the independent variables are considered to be exogenous while the dependent variable is actually considered to be endogenous. And that's why we say usually such things come as a result of endogenous sample selection and not necessarily as exogenous sample selection. And then we can have, for example, an example here where we can differentiate between exogenous sample selection and the endogenous sample selection. For example, with savings and income age, if we have such a function where we are basically saying saving is a function of income, age, and size. So if the sample was non-random, remember that because we are saying it's non-random, it's not random. It's one thing if we are dealing with random sampling, but if it's non-random, then what will happen is that certain age groups and income groups or even household size will either be over or under sampled. Okay, but now this will not really be a problem for the regression because it's really just examining the savings within the subgroups that are defined by these characteristics. Okay, so in other words, the distribution of these subgroups will not matter. But let us look at the wealth. Given the fact that we are estimating this variable, we want to get the average value of the wealth given education, experience, and age. So if this sample was non-random and certain individuals refused not to take part in that sample survey or whatever the case might be, so we will have a situation where it can either be high or low, and this will be result in a bias regression results because individuals might be systematically different from those who do not refuse to take part in the sample survey, right? And so that difference would have actually created better results or better estimation, okay? But uh, what if they are similar? Okay, so therefore, that's why we say in the case of the endogenous sample selection, we always have a problem if we are dealing with non-random sample selection. And therefore that part relates us to the outliers. Okay, remember that we talk about outliers, which are influential variables, and these are basically where you have extreme values. It's either you have some values that are extremely high, odd values. Okay, and this can actually result in in OLS estimation, because the outliers are extreme values. They can either be excessively high or extremely low, and some also can be as a result of us as we are inputting the data into the necessary Excel sheet, or it could be an issue of data generating process where probably the decision, and therefore that makes it very difficult whether we can discard or not discard the outliers. And so, for example, if you are taking a group of certain countries, you want to, maybe if you want to determine whether there is a relationship between sales and profitability, profit margins of certain firms when they or a relationship between research and development intensity vis-a-vis the firm size. So sometimes you might actually find that maybe if you take those firms, there's a possibility that maybe there is an outlier, okay? And this outlier might not necessarily be as a result of a mistake, but maybe some firms are really extremely have invested heavily in R&D, and you have an extreme different value. So usually that will distort the results of the in terms of averages, because all the other firms averages around this area and this firm is somewhere here. And if that's why if you compare regressions with outlier will be distorted compared to regressions with no outlier, because the one with no outliers sort of gives a true picture of what the average situation could be within the context. And lastly, so dealing with outliers, we can no longer estimate average values, but we can use the least absolute deviations. And this one, usually instead of dealing with minimizing the mean or the error, sorry, minimizing the error term, we actually have to we actually use we use the conditional median instead of using the conditional mean. Okay, because then that will give us a better estimation. And in this context, we also make use of quantile regression, okay, to estimate the condition quantiles or to estimate the parameters of the conditional quantiles. So I'm going to provide some examples using eViews on how to do some of the things that we have explained within this chapter. So this marks the end of this chapter for now.